This is Christine Johning in Lab M05 with my Lab 5 Motion of Falling Objects report. I made an observation. I took a video of a Kleenex falling and a water bottle falling. I modeled it and found that the main result was that the drag affects the movement of a falling object on Earth, such that gravity alone cannot predict the motion of the object. Here are the clips. I started the videos when the objects were in rest in my hand. I included the axes with the positive X to the right and the positive Y up. I also calibrated the video through the picture frame. The time between frames is 1/30th of a second, and the total time was under 2 seconds. The last frame is before the objects hit ground. So this is the movement of the Kleenex, and this is the movement of the water bottle. I looked up the mass of both objects. The initial positions came from the tracker data. Delta T was chosen, here is delta T, and it was chosen to be very small for both codes. The force of gravity equals the mass times gravity. In this case, it is not very useful to estimate the graph because the object does not follow the ideal path of something that would fall in a vacuum. For this reason, we must include drag. I am not showing the code without drag, since it is exactly the same, only a few lines are commented out. The force of drag equals the vector 0, velocity times b, 0, and the velocity is found using data from tracker. Final position minus initial position divided by the total time. This shows that the net force equals the force due to gravity plus the force due to drag. Here is the visualization of both objects. First, the Kleenex falling, and in this case, it falls straight down, and next, the water bottle falling. It also falls down. The model shows that the objects are moving downward, which corresponds to their movement in the video. The best way to compare the model without drag, the model with drag, and the experiment is to put the data and the predictions on the same graph. The lines match fairly well, so it is a good model for the experiment. So these are the experimental data, gravity alone, and gravity plus drag for the Kleenex, along with the water bottle. We have the experimental, gravity alone, and gravity plus drag. And since gravity alone and gravity plus drag are very similar, it shows that they are relatively the same in this small falling system. For the what does it mean question, for the object that drops slowly, examine the velocity versus time predicted by your model, with and without drag. Which models, if any, predict a terminal velocity? Discuss briefly. Terminal velocity is only reached when including the drag force in the model. This is due to the fact that the terminal velocity, by definition, means that the falling object has an upwards drag force that balances the downwards force from gravity. For the what if question, for the object that drops slowly, use your models, both with and without drag, to examine the object's velocity as a function of time in the case where the object is thrown downward initially instead of dropped from rest. In this case, does the object reach a terminal velocity? Examine both models with and without drag. Compare the terminal velocities, if any, in this case, and with the case where the object is dropped from rest. In this model, it takes longer, given that the amount of time in the experiment for the Kleenex to reach the terminal velocity. Since terminal velocity can only occur when the drag force balances the force due to gravity, the case when the Kleenex is dropped from rest will have to be able to reach a terminal velocity, whereas the case where the Kleenex is dropped will not be able to. Thank you very much for viewing my video.